Welcome all of you. I am Rosalind Mishra. Welcome to today's class of organic chemistry, wherein we shall be discussing about carboxylic acids. Now, in today's class, our major focus is going to be properties of or discussing or understanding the properties of carboxylic acids, effect of substituents on the acidity of carboxylic acids. Okay, so today's topic will be divided between two classes, wherein part 1 I shall be dealing with the properties and few topics related to acidity of carboxylic acids and effect of substituents. Rest we shall continue with our next class. As we had already discussed, under unit 5 we shall be covering or we shall be dealing with carboxylic acid per se and about amines, okay, that which is the aliphatic carboxylic acids and aliphatic amines. Under aliphatic carboxylic acids, we will be dealing with acidity of carboxylic acids, effect of substituents on acidity, okay, inductive effect, and we will look into a few qualitative tests for carboxylic acids. Apart from this, not only acids, we will also be looking into qualitative tests for amides and esters as well. Next, we will be looking into various structures and uses of a number of carboxylic acid derivatives like acetic acid, lactic acid, tartaric acid, citric acid, succinic acids, oxalic acids, salicylic acids, benzoic acids, benzyl benzoates, dimethyl phthalates, methyl salicylates and acetyl salicylic acids. Post this, we shall move into aliphatic amines. Under aliphatic amines also, we will be discussing a number of topics like basicity of amines, effect of substituents on basicity of amines, various qualitative tests of aliphatic amines. We will also be looking into few derivatives of amines. We will be learning their structures and their uses. For example, ethanolamine, ethylene diamine and amphetamine. Before that, let us first deal with our carboxylic acids or aliphatic carboxylic acids. Okay. So, now in today's class, we will be learning the various physical properties of carboxylic acids. Now, many carboxylic acids are colorless liquids with disagreeable odor. The carboxylic acids with 5 to 10 carbon atoms all have a goatee odor. Okay. These acids are also produced by the action of skin bacteria on human sebum or skin oils, due to which this goatee odor is produced, which this accounts for the odor of poorly ventilated locker rooms. The acids with more than 10 carbon atoms are wax like solids. Okay. So, the higher carboxylic acids are wax like solids and their odor diminishes. This goatee or unwanted odor reduces or diminishes as the molar mass increases. The resultant decreasing in volatility is the reason for this decrease in odor. Next, carboxylic acid molecules are polar. Okay. So, these are polar because of the presence of 2 electronegative oxygen atoms. So, if we talk about the properties of carboxylic acid, the first thing which comes into our mind is polarity. So, carboxylic acids are polar compounds. It is due to the presence of 2 electronegative oxygen atoms. Also, they participate in hydrogen bonding. They actively participate in hydrogen bonding because of the presence of hydroxyl group and the carbonyl group. So, apart from being polar molecules, carboxylic acid also participate in hydrogen bondings. It is due to the presence of this hydrogen bonding nature of carboxylic acids owes to the presence of two major functional group, which is hydroxyl group and the carbonyl group. Hydroxyl and the carbonyl group. These compounds form dimers when placed in non-polar solvents. Okay. So, when carboxylic acids are dissolved or placed in non-polar solvents, then dimerization happens. A phenomena called dimerization takes place. A phenomena called dimerization takes place. What is meant by dimerization? This means when carboxylic acid is placed in a non-aqueous solvent or a non-polar solvent, via hydrogen bonding, dimers are formed. This hydrogen bonding is between hydroxyl group of one carboxylic acid and the carbonyl group, okay, hydroxyl group of one carboxylic acid and the carbonyl group of other carboxylic acids. So, dimers are formed. The compound's solubility containing the carboxyl functional group in water depends on the size of the compounds. So, now moving on towards the factor of solubility. Okay. After polarity, let us move on to solubility. The compound's solubility containing the carboxyl functional group in water depends on the size of the compound, or it depends upon the alkyl group. The smaller the compound or shorter the alkyl group, higher will be the stability. But obvious, alkyl groups are non-polar, or the higher alkyl groups increases the carbon load, increases the carbon chain, due to which solubility decreases. Okay. So, when we talk about solubility of carboxylic acids, then depending upon the length of the alkyl chain, solubility varies. Lower the alkyl chain, higher is the stability. Longer the alkyl chain, lower is the stability. Now, moving on to boiling point. Moving on to another important parameter, which is boiling point. Generally, the boiling point of a carboxylic acid is higher than that of water. Okay. So, the boiling point of a carboxylic acid is more than that of water. Generally, they have a strong, okay. These compounds have the ability to donate protons, and thus they are Bronsted-Lowry acids. Because these are proton donors, okay. Being active proton donors, they are known as Bronsted-Lowry acids due to their ability to donate protons. Generally, they have a strong sour smell. Okay. Carboxylic acids have a very strong sour smell. Their esters, however, have a pleasant odor. Esters of carboxylic acids have a very pleasant fruity odor. Hence, they are used in perfumeries. Okay. Now, when we look into the physical properties again, while talking about polarity, they are polar compounds. Carboxylic acid, due to the presence of hydroxyl group and the carbonyl group, are polar in nature. Okay. When these carboxylic acids are placed in any non-aqueous solvent, they tend to dimerize. They tend to form dimers, wherein hydroxyl group of one acid forms a bond with the carbonyl group of another acid. Okay. So, dimerization happens. Further, when we talk about the solubility, then the solubility of carboxylic acids depends upon the alkyl side chain. Shorter the side chain, greater is the solubility. Longer the side chain, lower is the solubility. Next, while talking or while discussing about boiling point, generally the boiling point of carboxylic acid is higher than that of water. Okay. So, the boiling points of these acids are higher than water. Apart from this, carboxylic acids are also known as Bronsted-Lowry acids because they have the tendency to donate protons. Okay. Now, generally these acids have a strong sour smell, a disagreeable odor, but the esters of these carboxylic acids have a fruity pleasant odor. Hence, they are used in perfumeries. Next, as we have discussed earlier, carboxylic acids exhibit strong hydrogen bonding between the molecules. Okay. They show strong hydrogen bonding between molecules. Next, therefore, they have a high boiling point. Okay. So, the increased boiling point of carboxylic acid when compared to water owes to its nature or owes to its characteristic of forming strong hydrogen bond. Okay. So, it has the characteristic to form strong hydrogen bonds between molecules. This is when compared to other substance of similar molar mass. The carboxyl group readily engages in hydrogen bonding with water. Okay. So, carboxyl group very easily forms hydrogen bonds with water molecule. The acids with 1 to 4 carbon atoms are completely miscible with water. So, as we have already discussed earlier, lesser the number of carbon atoms, more will be the solubility. So, the miscibility in water increases between 1 to 4 carbon atoms. Solubility decreases as the carbon chain length increase. Okay. So, as the carbon chain length increases, this leads to decrease in solubility. It is because the dipole forces or the hydrogen bonding formation capacity become less important and dispersion forces becomes more prominent. Okay. So, as the alkyl chain length increases, as the chain or the length of alkyl chain increases, the dipole forces becomes less prominent and the dispersion forces becomes more prominent, thus leading to decrease in solubility. Okay. Next, palmitic acid. Okay. Palmitic acid is an important carboxylic acid having a molecular formula CH3, CH2 14 times, COOH. With its large non-polar hydrocarbon component, it is essentially insoluble in water. The carboxylic acids generally are soluble in organic solvents. Okay. So, palmitic acid essentially insoluble in water are definitely soluble in organic solvents such as ethanol, toluene and diethyl ether. Now, coming into the most important part about carboxylic acid or about the property of carboxylic acid, which is acidity of carboxylic acids. Okay. So, now we shall be discussing in detail about the acidity and effect of substituents on acidity of carboxylic acids. Carboxylic acid act as both hydrogen bond acceptors. It is because of carbonyl group. Okay. Due to the presence of C double bond O group, carboxylic acid act as hydrogen bond acceptors. They also act as hydrogen bond donor due to the presence of OH group. Okay. Hydrogen bond donor, and due to this group they act as hydrogen bond acceptor. Okay. Next, as a result, they often participate in hydrogen bonding. Okay. So, due to this, they tend to participate in hydrogen bonding. Carboxylic acids usually exist as dimeric pair in non-polar media because of their tendency to self-associate. Okay. Now, carboxylic acid has a tendency for self-association. They have a tendency to self-associate. Okay. This tendency to hydrogen bond gives them increased stability as well as higher boiling points relative to the acids in aqueous solution. Okay. So, this tendency to form a dimer or this tendency of dimerization helps the carboxylic acid for achieving higher boiling points in relation to the acids in aqueous solution. Next, moving on further, carboxylic acids are polar molecules. We have already discussed this point earlier. They tend to be soluble in water, but as the alkyl chain gets longer, the solubility decreases. It is due to increased hydrophobic nature of the carbon chain. Carboxylic acids are characterized as weak acids, okay, which means they cannot fully dissociate to produce H plus cation in neutral aqueous solution. Okay. So, these are known as weak acids. They are not strong acids. Carboxylic acids, since they cannot dissociate completely to give about H plus cation, therefore, they come under the category of weak acids. Okay. So, here if you see our C double bond O OH forms a dimer. Okay. They cannot completely dissociate, hence making them weak acids. Next, carboxylic acid have one property that distinguishes them from most other organic compounds. They are the acidic. Now, not as acidic as fuming sulfuric acid, but still pretty darned acidic. The acidity of this compound arises from the resonance stabilization of the conjugate base. Okay. So, these acids form conjugate base, that is, they are resonance stabilized. Okay. R C double bond O minus, this double bond shifts and the negative charge shifts, forming the second resonance stabilized structure. This is the first resonance stabilized structure, this is the second resonance stabilized structure. Okay. So, carboxylic acid is resonance stabilized, alright, hence imparting it an acidic nature, or the stability upon losing of hydrogen atom is more. Upon losing a hydrogen atom, carboxylic acid forms resonance stabilized structure. Okay. Hence imparting an acidic nature to these acids. Next, carboxylic acid undergo hydrogen bonding much like alcohols. However, in carboxylic acid you have both a hydrogen bond donor and a hydrogen bond acceptor in the same molecule. These acids thus form highly stable dimers, as we can see below. Okay. So, one of them is an hydrogen bond acceptor and one is a hydrogen bond donor. Thus, a stable dimer is obtained. Okay. Thus, a stable dimer is possible. Carboxylic acids undergo hydrogen bonding much like alcohols. However, in carboxylic acid, due to the presence of a hydrogen bond donor as well as a hydrogen bond acceptor, thus they form dimers, okay, which are stable or highly stable dimers. For small acids, these dimers cannot even be broken down by distillation. The bonds are so strong that in smaller molecules these dimers cannot even be broken down through distillation. The acidity of these compounds can be modified by changing the substituents on the alkyl portion of the acids. Electron withdrawing groups makes the molecule more acidic. Presence of electron withdrawing group makes the molecule more acidic by stabilizing the negative charge on the conjugate base, while electron donating group makes it less acidic by destabilizing the same charge. Okay. So, now if we look into factors that determine the strength of an acid, then this is the resonance stabilized structure. Okay. The ethanoate ion is strongly stabilized by two equivalent resonating structures. The ethanoate ion or the carboxylate ion is stabilized by two resonating structures. Both the carboxyl group and the carboxylate anion are stabilized by resonance, but the stabilization of the anion is much greater than that of the neutral functional group. In the carboxylate anion, the two contributing structures have equal weight in the hybrid and the CO bond are of equal length. This stabilization leads to a markedly increased acidity. Due to the resonance effect, phenyl or vinyl groups too increase acidity of carboxylic acids in spite of decreasing the acidity due to induction effect. Resonance stabilization of the carboxylate anion can be seen here. Next we will be discussing about inductive effect on acidity and basicity. Using the inductive effect, we can predict the acidity and basicity of compounds. As a generalization, it may be said that the electron withdrawing groups increase the acidity of a compound because it removes the hydrogen bond, thus leading to the resonating structure, and electron donating group decreases the acidity of a compound. It is because if we take the conjugate base of the acid, okay, if we take into account the conjugate base of the acid, that is RCOO minus, if R is an electron withdrawing group, then the conjugate base is stabilized via delocalization of the formed negative charge. If R had been electron donating, then the conjugate base would be destabilized because of interelectronic repulsion. Here if we can see, electron withdrawing group stabilizes the COO minus ion and increases acidity, okay, increases acidity, whereas an electron donating group destabilizes the COO minus ion and thus decreases acidity. Thus, it can be said that a negative inductive group decreases acidity or increases basicity, and a positive inductive and a negative inductive group increases acidity or decreases basicity of a compound. For example, if we take for example formic acid. Formic acid is more acidic than acetic acid due to positive inductive effect of the methyl group attached to the carboxylic acid group. Okay, because CH3 has a positive inductive effect, this decreases the acidity when compared to formic acid. Okay. So, this is how inductive effect also plays its role in determining the strength of acidity. There are two types of inductive effect, negative inductive effect and positive inductive effect. What is this negative inductive effect? When an electronegative atom such as halogen is introduced to a chain of atoms, the resulting unequal sharing of electrons generates a positive charge which is transmitted throughout the chain. This causes a permanent dipole to arise in the molecule, wherein the electronegative atom holds a negative charge and the corresponding effect is called the electron withdrawing inductive effect or the negative inductive effect. Whereas, when we talk about positive inductive effect, when a chemical species with tendency to release or donate electrons such as an alkyl group is introduced into a carbon chain, the charge is relayed through the chain and the effect is called a positive inductive effect. So, here we can see the effect of electron donating groups. Alkyl groups are the electron donating groups, they tend to push the electron away from themselves. This increases the electron density in the OH bond. The hydrogen bond is more strongly attached to the O atom, it is less likely to leave. So, the acid becomes weaker, whereas under electron withdrawing group it increases the acidity. Okay. Atomic radius also affect the strength of an acid. Greater the atomic radius, stronger is the acid. So, with this we end our today's class. In today's class we were discussing about properties of carboxylic acid, and we also learnt in detail about acidity and factors affecting the acidity of carboxylic acids. The same thing we shall continue in the next class, wherein we will be learning a lot more about carboxylic acids again. I hope the class was enjoying. Thank you.